Dear students, in our previous video, we saw the proof of this theorem where we divided the proof of this theorem into two parts, and then in the first part, again it is divided into two parts, in which we have already proved the first part in our previous video. Now let us continue to prove the second part. That is, we have to prove that alpha cut of A star B is a subset of alpha cut of A star alpha cut of B, for which we have to first consider an element from this set, and we have to prove that that element also belongs to this set. So let us take an element. Let Z be an element of alpha cut of A star B. So by the definition of alpha cut, what do we know? We know that the membership grade of that element with respect to the fuzzy set A star B will be greater than or equal to alpha. This is by the definition of alpha cut set. Now after this, we have already defined A star B of Z. So we get what is that actually? Supremum of minimum of A of Z, A of X, comma B of Y, where Z is equal to X star Y, and this is greater than or equal to alpha. So this we have substituted this, which is greater than or equal to alpha. So now next, moreover, we can choose for any n greater than integral part of 1 by alpha plus 1. Now what is this integral part of 1 by alpha? It means that it is the largest integer that is less than or equal to alpha. So that is the integral part. So if we take an n like this, then there exists xn and yn. So this is in general, x is in general. Now xn and yn are particular values where we have chosen that n to be greater than integral part of 1 by alpha plus 1. So xn and yn such that z will be equal to xn star yn, and the minimum of the membership grades of these two. So A of xn comma B of yn will be greater than alpha minus 1 by n, because we know that the supremum of the minimum of A of x comma B of y is greater than or equal to alpha. Now actually the supremum of these minimum of these two values, that is, we will be having x0, x1, x3, etc., xn values. Similarly, we will be having y0, y1, y2, etc. So out of those values, we have to choose. For example, if it is A of x0 and y0, then we have to choose the minimum of those two values. Similarly, A of x1 and B of y1. Out of those two, we have to choose the minimum. Then A of x3 and B of y3, for example. Like that, we have to A of xn comma B of yn. So we will be choosing the minimum of those values. So we will have a set of values out of which we will choose a maximum. So that value will be greater than or equal to alpha. So now we are taking for a particular value xn and yn. That is the minimum of these two. It will be definitely greater than alpha minus 1 by n, because we have chosen alpha n in this way. So that is greater than alpha minus 1 by n. For example, you can just imagine like the highest value that alpha could take is alpha is an element of open interval 0 and closed interval 1. The highest value alpha could take is 1. So 1 divided by 1 will be 1 only. That is the largest integer. And then 1 plus 1 is 2. So the value of n will be greater than 2. So it will be 3, 4, 5, etc. like that. So when we substitute, we have chosen alpha to be 1. So we have to check here 1 minus 1 by 3. And similarly, the next value when n is equals to 4, it will be 1 minus 1 by 4. n equal to 5, 1 minus 1 by 5. If we observe, we see that definitely this minimum of these two values will be greater than that value. You can make a check in a rough work. So the minimum of these two values is greater than this. So in fact it can be greater than or equal to also sometimes. So the minimum of these two values is greater than or equal to this, which means that if suppose a of xn is the minimum value, a of xn will be greater than or equal to alpha minus 1 by n. If the minimum of these two is itself greater than this value, then the other one will be the maximum value, and that will also be definitely greater than or equal to alpha minus 1 by n. Okay, now we have a of xn to be greater than or equal to alpha minus 1 by n. That is, the membership grade of xn with respect to the fuzzy set A is greater than or equal to alpha minus 1 by n. So what does this imply? Alpha minus 1 by n cut of A. That is, xn will be an element of, I missed it here, xn will be an element of alpha minus 1 by n cut of A, because of the definition of alpha cut. Okay, and here what does this imply? Yn will be an element of alpha minus 1 by n beta cut. Okay, so therefore a of xn, that is the membership grade of xn, greater than with respect to the fuzzy set A, greater than or equal to alpha minus 1 by n, imply that alpha minus 1 by n cut of A, that is xn will be an element of alpha minus 1 by n cut of A, and the membership grade of yn with respect to the fuzzy set B is greater than or equal to alpha minus 1 by n, implies that yn is an element of alpha minus 1 by n cut of B. So this is by the definition of alpha cut sets. So these are two particular xn and yn. Now we will consider sequences, that is, we will consider sequence xn and sequence yn. So now it's not a single value, it is a sequence of values. And also we can observe that here we have alpha minus 1 by n, and this will be lesser than or equal to alpha minus 1 by n plus 1. I am increasing the denominator here by 1. So what will happen? Definitely this value gets increased, and when we subtract this value gets decreased actually, because the denominator is being increased. So when we subtract a higher value from alpha, that will be greater than this, that is this value actually is decreased. I'm sorry, here we increase the denominator. So the thing is, here we have 1 by n, and here we have 1 by n plus 1. This value is lesser than this value. This 1 by n plus 1 is lesser than 1 by n, because as the denominator gets increased, this value changes, right? So this value is lesser than this value. So from alpha we are subtracting a value which is lesser than this. So this value will be on the whole, that results will be lesser than or equal to this full value. Maybe you can just give values to alpha and n and you can check this. So now we obtain this. And now here we are going to use a theorem which we have seen in our previous sections. That is, in our previous section we saw that if alpha is lesser than or equal to beta, so if alpha is lesser than or equal to beta, then beta cut of a fuzzy set A will be a subset of alpha cut of A. This theorem we have already proved in our previous sections. So this theorem we will be utilizing here. So now using this theorem, here we can consider this value like alpha and this as beta. Now because we have this, from this we can say that this one, that is alpha minus 1 by n plus 1 cut of A, will be a subset of alpha minus 1 by n cut of A. And also similarly we can do it for the fuzzy set B. So alpha minus 1 by n plus 1 cut of B, okay, will be a subset of alpha minus 1 by n cut of B. And these two sequences xn and yn are closed intervals, because of which we can observe that the sequence xn and the sequence yn are bounded, because if it is closed we know the lower bound and we know the upper bound. So if we know the lower bound and upper bound, then we call that sequence to be a bounded sequence. So therefore xn and yn are bounded sequence. And we know that bounded sequence need not be convergent, but there is a theorem in analysis which says that every subsequence of a bounded sequence is a convergent sequence. That is, every bounded sequence has a convergent subsequence. So that is the concept that we know from analysis. So now for the sequence xn, let x n comma I be a subsequence which converges to a point x0, and for this let y n comma I be a subsequence that converges to y0. Now this subsequence again has a subsequence which is also convergent to the same point. So we just want to show that the subsequence also converges to x0. So that is by the analysis. So n comma I comma, the subsequence can be taken as j, and that converges to x0, and similarly y n comma I comma j converges to y0. We have used this by using the concept that every bounded sequence has a convergent subsequence, and that convergent subsequence we are taking another sequence which is also convergent to the same point. So we just want to show that how much ever sequences we derive from it, all those sequences converges to that same point. So so finally we arrive at two sequences x n I comma j and y n I comma j, which converges to x0 and y0 respectively, and also x n comma I comma j star y n comma I comma j will be equal to z. Now in this we shall apply a limit for z, I mean a j. So z will be equal to, I am considering a limit j tends to infinity for this fully. So x n comma I comma j star y n comma I comma j. So now that will be equal to, we can separate the limits. So we can write this as limit j tends to infinity of x n comma I comma j star limit j tends to infinity of y n comma I comma j. So now when we apply the limit, we know that this converges to x0. So this will be equal to x0 star, and this converges to y0. So because we know that, so this will be y0. So therefore z, from this we have arrived that z is equals to x0 star y0. Also by using this, that is, we know that here we have a of xn is greater than or equal to alpha minus 1 by n. So by using this we can say that a of x n comma I comma j will be greater than or equal to alpha minus 1 by n comma I comma j. And here b of y n comma I comma j will be greater than or equal to alpha minus 1 by n comma I comma j. So let me write that. So this implies that a of x n comma I comma j is greater than or equal to alpha minus 1 by n comma I comma j, and also b of b of y n comma I comma j will be greater than or equal to alpha minus 1 by n comma I comma j. And now we know that a of x0 is what? The limit of this. So a of x0 is equal to, this x0 can be written as a of limit j tending to infinity x n comma I comma j, because we know that x0 is the limit of this. So this can be written as a of x0 can be written as a of this. Now this limit can be taken out. So limit j tending to infinity, and this can be written as a of x n comma I comma j. So this can be written like this. But what is a of x n comma I comma j? It is greater than or equal to alpha minus 1 by n comma I comma j. So this is greater than or equal to limit j tending to infinity. So we will replace it by alpha minus 1 by n comma I comma j. So now if this is infinity, so this full term will become 0. It's actually the jth position. So this term will become 0, and so it will be only alpha, and so this will be equal to alpha. So therefore from this we obtain that a of x naught is greater than or equal to alpha. So what do we infer from this? X naught is an element of alpha cut of a. Now similarly we can take b of y naught. In a similar manner it will be equal to b of limit j tending to infinity then y n comma I comma j, and that will be equal to, taking the limit out, j tending to infinity, this will be b of y n comma I comma j. And what is this? This is greater than or equal to limit j tending to infinity, and using this we obtain here to be alpha minus 1 by n comma I comma j. And this becomes 0 as j tends to infinity. This term gets 0. So this will be equal to alpha. So we observe from this that b of y naught is greater than or is greater than or equal to alpha. And so this implies that y naught is an element of alpha cut of b. So this we have obtained. So therefore from this we can say that, so therefore there exists some there is x naught element of alpha cut of a and y naught element of alpha cut of b, such that z is equal to x naught star y naught. So that is this implies that z is an element of alpha cut of a star alpha cut of b. So thus we started with an element from alpha cut, that is here. We started z to be an element of alpha cut of a star b, and we have proved that z is an element of alpha cut of a star alpha cut of b, which implies that alpha cut of a star b is a subset of alpha cut of a star alpha cut of b. That is, we are done with the second part of the proof. So we have proved this. So by this we have proved that a star b is a fuzzy number. So this implies a star b is a fuzzy number. So are we done with the total proof of the theorem? No, not yet, because we have proved only that a star b is a fuzzy number. So this is done. So we are yet to prove that a star b is continuous, the proof of which will be continued in our next video. Hope you have understood this theorem. It's a very significant theorem in the examination point of view. Thank you.